Look up at the night sky on a clear evening, away from city lights. You might see a faint milky band stretching across the darkness. That's our home galaxy, the Milky Way, containing somewhere between 200 and 400 billion stars. It's vast beyond human comprehension, measuring roughly 100,000 light years from edge to edge. If you could travel at the speed of light, it would take you 100,000 years to cross from one side to the other. Now imagine a galaxy so large that the Milky Way would look like a small island next to a continent. A galaxy so enormous that if you placed our entire galactic home at one end, you'd need to travel 16 million light years to reach the other side. That's not 16 million miles or 16 million kilometers. That's 16 million years of traveling at the speed of light, the fastest speed possible in the universe. This galaxy exists. It's real. And in February of 2022, astronomers confirmed its discovery using radio telescopes that can see things invisible to our eyes. The galaxy is called Alcyoneus, named after a giant from Greek mythology, and it is the largest galaxy structure ever found by human beings. But to truly understand what makes Alcyoneus so extraordinary, we need to start at the beginning and build our way up, because the story of the biggest galaxy is really the story of how we learned to see the invisible, measure the immeasurable, and comprehend scales that break our ability to visualize. If you find this kind of deep exploration interesting, hitting the like button helps the algorithm show this to other curious people. Now, let's begin our journey from the familiar to the absolutely mind-bending. When you look up at the night sky and see that band of light we call the Milky Way, you're seeing our galaxy from the inside. It's like trying to understand the layout of a city when you're standing in the middle of it. You can see buildings around you, streets nearby, but the overall structure is hard to grasp. For most of human history, we didn't even know we were inside a galaxy. We just saw a lot of stars. The ancient Greeks saw that milky band across the sky and created myths to explain it. One story said the goddess Hera was nursing the infant Heracles, and when he bit down too hard, milk sprayed across the heavens. That's where we get the name Milky Way from the Latin Via Lactea, the road of milk. They had no idea they were looking at billions of stars so distant they blurred together into a glowing river. It wasn't until the early 1600s that Galileo pointed one of the first telescopes at the Milky Way and discovered something shocking. That glowing band wasn't a cloud or mist. It was made of countless individual stars, so numerous and so faint that they blended together when viewed with the naked eye. This was revolutionary. The universe suddenly contained far more stars than anyone had imagined. But even Galileo didn't understand what he was looking at. He knew there were many stars, but he didn't know they were organized into a massive rotating disk. He didn't know we were inside that disk, looking at it edge on. He couldn't have known because the tools didn't exist yet to measure such vast distances or understand such enormous structures. The concept of galaxies as we understand them today is surprisingly recent. In the 1700s and 1800s, astronomers using increasingly powerful telescopes started noticing fuzzy patches in the sky. They called these nebulae, from the Latin word for cloud. Some nebulae were in our own galaxy, clouds of gas and dust where new stars were forming, but others looked different. They had structure, spiral shapes, distinct forms that didn't quite match the gas clouds. In 1781, the French astronomer Charles Messier compiled a catalogue of these fuzzy objects. He was actually hunting for comets and wanted to record everything that looked fuzzy but wasn't a comet, so he wouldn't waste time observing the same objects over and over. His catalogue listed 110 objects, many of which we now know are galaxies. The Andromeda Galaxy, our nearest large galactic neighbour, was number 31 in his catalogue, which is why astronomers still call it M31. But here's what's remarkable. Messier looked at M31 and had no idea it was another galaxy. He thought it was just a nebula, a cloud of gas within our own stellar system. The technology didn't exist to resolve it into individual stars. He could see it was shaped like a spiral, but he didn't know what that meant. He was looking at an entire galaxy containing hundreds of billions of stars, and he thought it was a fuzzy cloud. This confusion lasted for over a century. Through the 1800s and into the early 1900s, astronomers debated what these spiral nebulae actually were. Some thought they were solar systems in the process of forming disks of material that would eventually condense into stars and planets within our own galaxy. Others suspected they might be separate systems entirely, island universes as they called them, but the evidence was inconclusive. The debate came to a head in 1920 in what's now called the Great Debate. Two prominent astronomers, Harlow Shapley and Heber Curtis, publicly argued about the nature of spiral nebulae. Shapley argued they were within the Milky Way. Curtis argued they were separate galaxies far beyond our own. Both presented evidence. Both made compelling cases, and both were partly right and partly wrong about various details. The issue was finally settled in the 1920s by Edwin Hubble, the astronomer after whom the Hubble Space Telescope is named. Hubble had access to the most powerful telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson in California. This telescope was large enough and its optics sharp enough to resolve individual stars in some of the spiral nebulae. In 1923 and 1924, Hubble identified Cepheid variable stars in the Andromeda Nebula. Cepheid variables are stars that brighten and dim in a regular pattern, and the period of that pattern is directly related to the star's intrinsic brightness. By measuring how long a Cepheid takes to cycle from bright to dim and back, you can calculate how luminous it actually is. Then by comparing that to how bright it appears from Earth, you can determine its distance. It's like seeing a light bulb from far away. If you know it's a 100-watt bulb and you measure how bright it looks, you can figure out how far away it is. A 100-watt bulb that appears very dim must be far away. A 100-watt bulb that appears bright must be close. Cepheid variables are cosmic light bulbs, where we can determine the wattage by timing their flicker. The relationship between a Cepheid's period and its luminosity was discovered by Henrietta Swan Leavitt in 1912. Leavitt worked at Harvard College Observatory as a human computer, one of many women who analyze photographic plates of the sky. She studied Cepheid variables in the Small Magellanic Cloud, a nearby dwarf galaxy that orbits the Milky Way. Because all the stars in the Small Magellanic Cloud are roughly the same distance from Earth, Leavitt could compare the apparent brightness of different Cepheids directly. She noticed that brighter Cepheids had longer periods. The relationship was clear and consistent. A Cepheid with a 10-day period was intrinsically brighter than one with a 5-day period. This meant you could use the period as a ruler. Measure the period, calculate the true brightness, compare to the apparent brightness, and determine the distance. It was brilliant and elegant, and it became one of the most important tools in astronomy. Hubble's calculations using Leavitt's period luminosity relationship showed that the Cepheids in Andromeda were about 900,000 light-years away. This distance has since been refined to about 2.5 million light-years. But even Hubble's initial estimate made one thing absolutely clear. Andromeda could not possibly be inside the Milky Way. It was too far away. It had to be a separate system entirely, an island universe, a galaxy in its own right. This discovery fundamentally changed our understanding of the cosmos. We went from thinking the Milky Way was essentially the entire universe, with everything we could see part of it, to realizing that the Milky Way was just one galaxy among many. It was like discovering that your town isn't the whole world, but just one settlement on a planet full of them. And once astronomers started looking, they found galaxies everywhere. Point the telescope at any dark patch of sky and you'd find them. Hundreds, thousands, eventually millions of galaxies scattered throughout the observable universe, each one containing billions or hundreds of billions of stars, each one a massive system like our own Milky Way. But not all galaxies look the same. As telescopes improved and astronomers catalogued more and more of these systems, they noticed distinct types. Some galaxies have beautiful spiral arms like the Milky Way and Andromeda, arms of stars and gas sweeping out from a central bulge in graceful curves. These are spiral galaxies, and they come in different varieties. Some have tight, well-defined arms. Others have looser, more fragmentary arms. Some have a bar-shaped structure running through their center, with the arms extending from the ends of the bar. Our own Milky Way is actually a barred spiral galaxy. Other galaxies have no spiral structure at all. They're shaped like ellipsoids, basically stretched out spheres or football shapes. These elliptical galaxies range from nearly spherical to highly elongated, and they tend to be smoother and more uniform than spiral galaxies. They contain older stars and less gas and dust for forming new stars. Many of them are the result of galactic mergers, two or more galaxies that collided and merged together over hundreds of millions of years. Then there are irregular galaxies, systems with no clear structure at all. They're chaotic, lumpy, often the result of gravitational interactions with other galaxies that have disrupted their original shapes. The Large and Small Magellanic Clouds, two small galaxies that orbit the Milky Way and are visible from the southern hemisphere, are classified as irregular galaxies. As astronomers studied these different types, they started asking questions about size. How big are galaxies? What's the range? Are they all roughly similar, or do they vary wildly? And most importantly, for our story, what's the largest galaxy that exists? To answer that question, we need to understand what we mean by the size of a galaxy, and that's more complicated than you might think. Galaxies don't have sharp edges. They're not like countries with defined borders. They fade out gradually. The density of stars decreases as you move away from the center, until eventually you reach regions where there are so few stars that it's hard to say whether you're still in the galaxy or in the empty space between galaxies. Think of it like a campfire. Close to the flames, there's clearly fire. Farther out, there are sparks and embers. Even farther out, there might be smoke or warm air. At what point does the campfire end? It depends on what you're measuring. Are you measuring the flames, the heat, the smoke, the light? For galaxies, astronomers typically define size by measuring out to a certain level of brightness or stellar density. A common approach is to measure the radius at which the galaxy's brightness drops to a specific fraction of its peak brightness. But different types of galaxies need different definitions, and this becomes important when we start talking about the biggest galaxies, because some of them have structures that extend far beyond their visible stars. In the early days of galaxy research, astronomers measured what they could see with optical telescopes that detect visible light. The biggest galaxies by this measure turned out to be giant elliptical galaxies found at the centers of galaxy clusters. These are enormous systems containing trillions of stars, far larger than the Milky Way. One of the most famous is M87, a giant elliptical galaxy in the Virgo cluster, about 54 million light-years from Earth. M87 contains several trillion stars and measures roughly 240,000 light-years across, about 2.5 times wider than the Milky Way. That's enormous, but as telescopes improved, astronomers found even larger galaxies. IC1101, a galaxy in the Abell 2029 galaxy cluster roughly 1 billion light-years away, was long considered the largest known galaxy. Early measurements suggested it might be 6 million light-years across, absolutely dwarfing the Milky Way. More recent observations have revised that estimate downward to somewhere between 2 and 4 million light-years, still enormous, but not quite as monstrous as initially thought. The uncertainty shows how difficult these measurements are at such distances. But here's where the story takes a turn. All of these measurements were based on optical observations, looking at the stars that make up the visible portion of galaxies. In the mid-20th century, astronomers developed a new tool that would reveal structures invisible to optical telescopes: radio astronomy. Radio waves are a form of light, just like visible light, but with much longer wavelengths. Our eyes can't detect radio waves, but specially designed telescopes can. And it turns out that many things in the universe emit radio waves, including hot gas around black holes, supernova remnants, and certain types of astronomical phenomena that are dim or invisible in visible light. The development of radio astronomy is a fascinating story in itself. It began almost by accident in the 1930s, when Carl Jansky, a physicist working for Bell Telephone Laboratories, was investigating sources of radio static that might interfere with radio telephone service. He built a large directional antenna and systematically searched for sources of interference. Jansky found 3 types of static. Nearby thunderstorms produced one type. Distant thunderstorms produced another, but there was a 3rd type of static that was persistent and seemed to come from a specific direction in the sky. Over weeks of observation, Jansky noticed that this direction changed in a predictable pattern, completing a full cycle every 23 hours and 56 minutes. That's the length of a sidereal day, the time it takes Earth to rotate once relative to the distant stars. Jansky realized he was detecting radio waves from space. Further analysis showed the signal was strongest when his antenna pointed toward the center of the Milky Way. He had discovered cosmic radio emission. Jansky published his findings in 1933, but the astronomical community was slow to follow up. Radio astronomy required different equipment and different expertise than optical astronomy, and most astronomers didn't have access to the necessary technology. It wasn't until after World War II, when military radar technology became available for civilian use, that radio astronomy really took off. Starting in the 1950s and 60s, radio astronomers began systematically surveying the sky with these new instruments. They pointed their radio telescopes at known galaxies and discovered something surprising. Many galaxies, especially large elliptical galaxies, weren't just the compact systems visible in optical light. They had enormous structures extending far beyond their visible edges. These structures are called radiolobes or jets, and they're produced by supermassive black holes at the centers of galaxies. Here's how they work. Most large galaxies have a supermassive black hole at their center, an object with the mass of millions or billions of stars compressed into a region smaller than our solar system. These black holes are usually quiet, just sitting there not doing much. But sometimes they start feeding. When gas and dust fall toward a supermassive black hole, it doesn't fall straight in. It spirals, forming an accretion disk, a rotating disk of material that gets hotter and denser as it approaches the black hole. The physics of this accretion disk can launch jets of material perpendicular to the disk, shooting outward at speeds approaching the speed of light. These jets contain charged particles, mostly electrons and protons, moving at relativistic speeds. As they plow through the surrounding space, they create enormous bubbles or lobes of material that emit radio waves. The jets can extend for hundreds of thousands or even millions of light years beyond the galaxy itself, creating structures vastly larger than the visible galaxy. Imagine if the Milky Way had jets extending 1 million light years on either side. The visible galaxy would be like a small hub, with 2 enormous wings stretching out into the void. That's what many large galaxies look like in radio wavelengths. One of the first and most famous examples is Cygnus A, a galaxy about 600 million light-years from Earth. In optical light, it looks like a fairly normal elliptical galaxy. But in radio wavelengths, it has two massive lobes extending about 230,000 light-years from the galaxy's center on either side. The total radio structure spans roughly 500,000 light-years, far larger than the visible galaxy itself. Cygnus A was discovered in 1939 by Grote Reber, an amateur radio astronomer who built his own radio telescope in his backyard in Wheaton, Illinois. Reber was inspired by Jansky's work and decided to follow up with a more systematic survey. He built a 30-foot diameter dish antenna and used it to map the radio sky. Reber's telescope was primitive by modern standards, but it was sensitive enough to detect several bright radio sources. The brightest source in the constellation, Cygnus, he called Cygnus A. For years, no one knew what Cygnus A was. It was too faint to see in optical light, and its exact position was uncertain given the low resolution of early radio telescopes. It wasn't until 1951 that astronomers using new radio interferometry techniques precisely located Cygnus A and pointed optical telescopes at that position. They found a faint, peculiar-looking galaxy. Spectroscopic analysis showed it was very distant, about 600 million light-years away. To be detectable at that distance, despite being so faint in optical light, Cygnus A had to be extraordinarily luminous in radio wavelengths. Further observations revealed the double-lobed structure. The galaxy was shooting jets of material outward, creating two enormous bubbles that dwarfed the visible galaxy. This was one of the first clear examples of a radio galaxy, and it opened astronomers' eyes to the possibility that galaxies could have structures much larger than their visible components. Throughout the latter half of the 20th century, astronomers discovered more and more of these radio galaxies with enormous jet structures. They found galaxies with jets stretching 1 million light-years, then 2 million, then 3 million. Each new discovery pushed the boundaries of what we thought was possible. But there was a problem. These jets and lobes are difficult to see. They emit radio waves, but those radio waves are faint, spread out over enormous volumes of space. To detect them, you need sensitive radio telescopes and long observation times. And even then, you can easily miss structures that are particularly faint or extended. Think about trying to see a very large, very faint object against a dark background. It's easy to miss if you're not looking carefully, or if your instruments aren't sensitive enough. For decades, astronomers knew they were probably missing some of the largest structures in the universe simply because they couldn't detect them with the available technology. That brings us to modern radio astronomy and the telescopes that have revolutionized the field. The most important for our story is the Low Frequency Array, or LOFAR, a network of radio telescopes spread across Europe. LOFAR is different from traditional radio telescopes. Instead of one large dish, it uses thousands of small antennas working together, combining their signals to create the equivalent of a telescope much larger than any single dish could be. LOFAR operates at low frequencies, detecting radio waves with wavelengths of several meters. This makes it particularly good at seeing the faint, extended structures around galaxies that higher frequency telescopes might miss. And because it's a network of telescopes spread across multiple countries, it has excellent resolution, the ability to distinguish fine details in the radio sky. The design of LOFAR is elegant in its simplicity. The individual antennas are just metal wires arranged in specific patterns. There are no moving parts, no large dishes to point at the sky. Instead, the telescope steers electronically, combining signals from different antennas with computer-controlled delays to look at different parts of the sky without physically moving anything. This makes LOFAR incredibly flexible. It can observe multiple targets simultaneously by processing the data in different ways. It can create wide field images covering large portions of the sky. And it can operate continuously, building up sensitivity over long observation periods. In the 2000s, LOFAR began systematic surveys of the radio sky, mapping hundreds of thousands of radio sources with unprecedented sensitivity. The data from these surveys is enormous, requiring powerful computers and sophisticated algorithms to process. Astronomers download the observations and spend months or years analysing them, looking for interesting objects and structures. And that's exactly what Martijn Oey, a PhD student at Leiden University in the Netherlands, was doing in the early 2000s. Oey was studying radio galaxies, particularly the largest ones with the most extended jets. He was interested in understanding how these giant structures form, how long they last, and what they tell us about the evolution of galaxies and black holes. In February of 2022, Oey and his colleagues published a paper announcing the discovery of the largest known galaxy structure ever found. They had been analysing LOFAR data from a survey of a region of the sky when they noticed something extraordinary, a radio galaxy with jets extending far beyond anything previously observed. The galaxy is called Alcyoneus, and its radio lobes span approximately 16.3 million light-years from end to end. To put that in perspective, the distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years. The jets of Alcyoneus could span the distance between the Milky Way and Andromeda more than 6 times over. If you place the Milky Way at one end of Alcyoneus's radio structure and started travelling at the speed of light toward the other end, you would travel for 16.3 million years before you reached it. The light we see from the far end of Alcyoneus's jets was emitted when our distant ancestors were just beginning to diverge from other primates. Modern humans didn't exist yet. The continents were in different positions. The Earth was a completely different place. Alcyoneus is not just large, it's almost incomprehensibly large. And before we dive deeper into what makes it so special and how it formed, we need to take a step back and really understand what 16 million light-years means, because numbers this large break our ability to visualize them. We need to build up to it gradually, starting from scales we can understand and working our way up. Let's start with something familiar. The Earth. Our planet has a diameter of about 12,742 kilometers, or roughly 7,918 miles. If you got in a car and could somehow drive around the equator at highway speed, about 100 kilometers per hour, it would take you roughly 400 hours of continuous driving to circle the globe. That's a little over 16.5 days of non-stop driving. The Earth seems large when you're standing on its surface. You can't see the curvature from ground level. The horizon looks flat. But from space, Earth's true size becomes apparent. The International Space Station orbits at an altitude of about 400 kilometers. From that height, astronauts can see about 3% of Earth's surface at once. They watch entire countries slide past in minutes. Thunderstorms that would dominate local weather for hours appear as small swirls in the cloud patterns. The Earth is revealed as a finite object, a sphere floating in the void. Now let's go bigger. The Moon orbits Earth at an average distance of 384,400 kilometers. The Apollo astronauts who traveled to the Moon in the late 1960s and early 1970s took about 3 days to make the journey using some of the most powerful rockets ever built. The distance from Earth to the Moon is so large that you could fit all the other planets in our solar system between Earth and the Moon with room to spare. Jupiter's diameter is about 140,000 kilometers. Saturn is about 120,000 kilometers. Add them all up and you get roughly 380,000 kilometers, just barely fitting in the space between us and our closest celestial neighbor. When the Apollo astronauts were traveling to the Moon, they experienced something profound. For the first part of the journey, Earth filled their windows, a blue and white sphere growing smaller behind them. The Moon ahead was just a bright disk, not yet showing much detail. But there came a point, about 346,000 kilometers from Earth, where the gravitational influence of Earth and Moon balanced. Past this point, called the Hill sphere, or the point of equal gravitational attraction, the Moon's gravity became dominant. The spacecraft began accelerating toward the Moon rather than decelerating away from Earth. The astronauts described crossing this invisible boundary with reverence. They were no longer Earthlings journeying outward. They were the first humans to enter another world's gravitational domain. Now we'll jump to the Sun. Our star sits about 150 million kilometers from Earth. This distance is called an astronomical unit, and it's so large that we use it as a standard measurement in the solar system. When you read that Mars is 1.5 astronomical units from the Sun, that means it's 1.5 times farther from the Sun than Earth is, roughly 225 million kilometers. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. When you look at the Sun, you're seeing it as it was 8 minutes ago. If the Sun suddenly disappeared, we wouldn't know for over 8 minutes, because the information about that disappearance would travel toward us at the speed of light, taking 8 minutes to cover the distance. Actually, the situation is more interesting than simple disappearance. If the Sun vanished, we wouldn't just lose its light after 8 minutes, we'd also lose its gravitational pull at exactly the same moment. According to Einstein's theory of general relativity, gravitational effects propagate at the speed of light, the same speed as electromagnetic radiation. So 8 minutes and 20 seconds after the Sun disappeared, we'd simultaneously experience 3 things. The sky would go dark as the last light from the Sun arrived. Earth would stop orbiting and begin moving in a straight line, tangent to its former orbital path. And we'd notice that the Sun was gone. All 3 effects would happen at the same instant because they all travel at light speed. This introduces one of the most important concepts in astronomy, the light year. A light year is not a measure of time despite having year in the name. It's a measure of distance, specifically the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, and in 1 year it covers approximately 9.46 trillion kilometers. When we say a star is 4 light years away, we mean that the light we see from that star left its surface 4 years ago. We're looking into the past. The star could have changed. It could have dimmed or brightened or even exploded. We wouldn't know for 4 years because the light carrying that information is still traveling toward us. The speed of light isn't arbitrary. It's woven into the fabric of space-time itself. In Einstein's special theory of relativity, the speed of light appears as a fundamental constant that's the same for all observers regardless of their motion. This leads to strange consequences. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour relative to the train, someone standing on the ground would see the ball moving at 150 kilometers per hour. Velocities add. But light doesn't work this way. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, you might expect the light to move at 1.5 times the speed of light relative to a stationary observer. But it doesn't. Both you and the stationary observer measure the light moving at exactly the same speed, 300,000 kilometers per second. The speed of light is invariant. This seems impossible until you realize that space and time adjust to keep light speed constant. Moving clocks run slow. Moving objects contract in the direction of motion. These aren't optical illusions. They're real physical effects that have been measured countless times in particle accelerators, with atomic clocks on airplanes, with GPS satellites, and through astronomical observations. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. That's roughly 40 trillion kilometers. If you could travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, at about 192 kilometers per second, it would still take you about 6,800 years to reach Proxima Centauri. With current technology, the nearest star is effectively unreachable within a human lifetime. But Proxima Centauri isn't just far away. It's also very different from our Sun. It's a red dwarf star, much smaller and cooler. It has about 12% the mass of the Sun and about 15% of the Sun's radius. If you replace the Sun with Proxima Centauri, the star would only extend about halfway from the Sun's current center to its current surface. It would be much dimmer too, shining with only about 0.17% of the Sun's luminosity. Despite being so dim, Proxima Centauri is actually more representative of stars in our galaxy than the Sun is. About 75% of all stars in the Milky Way are red dwarfs. They're common because they're the smallest stars that can sustain hydrogen fusion. Any smaller, and they'd be brown dwarfs, failed stars that never quite ignited fusion in their cores. Red dwarfs are also incredibly long-lived. The Sun will burn for about 10 billion years total before exhausting its fuel. Proxima Centauri will burn for trillions of years. The smallest red dwarfs could last for tens of trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed is still shining today because the universe simply hasn't existed long enough for any of them to die. Our galaxy, the Milky Way, is roughly 100,000 light years across. If you could somehow travel at the speed of light, which you can't, it would take you 100,000 years to cross from one edge to the other. The light we see from stars on the far side of the galaxy left those stars 100,000 years ago, when modern humans were just beginning to migrate out of Africa. The Milky Way contains somewhere between 200 and 400 billion stars. These stars are not evenly distributed. Most of them cluster in a disk shape with a bulge at the center. If you could view the Milky Way from outside, from above or below the disk, you'd see a spiral structure with distinct arms of stars and gas curving out from the central bulge. From the side, you'd see a relatively thin disk with a bright center and dimmer edges. The disk is about 1,000 light years thick in the galactic plane where most stars reside, but the distribution of stars extends farther above and below the plane in what's called the galactic halo. The halo contains old stars and globular clusters, spherical collections of hundreds of thousands of ancient stars orbiting the galactic center in elongated paths that take them high above and below the disk. Our Sun sits about 26,000 light years from the galactic center, roughly halfway out from the center to the edge. We're in one of the spiral arms called the Orion Spur, or the Orion Arm. The entire solar system orbits the galactic center at a speed of about 828,000 kilometers per hour. At this speed, it takes roughly 225 to 250 million years for us to complete one orbit. The last time we were in our current position, dinosaurs were just beginning to appear on Earth. Think about what that means. The Sun has completed about 20 orbits around the galaxy since it formed 4.6 billion years ago. During those 20 orbits, the solar system has witnessed the entire history of complex life on Earth. Single-celled organisms evolved into multicellular life. Plants colonized the land. Animals followed. Dinosaurs rose and fell. Mammals diversified, and humans emerged. All of that happened while the Sun traced 20 loops around the galactic center, sometimes passing through spiral arms where star formation is active, and supernovae are more common, sometimes drifting through quieter regions between the arms. Some scientists have speculated that mass extinctions on Earth might correlate with passages through spiral arms, though the evidence is controversial. Now let's zoom out further. The Andromeda Galaxy, our nearest large galactic neighbor, sits about 2.5 million light years away. The light we see from Andromeda left that galaxy 2.5 million years ago when our ancestors were primitive hominids in Africa, using stone tools and living in small groups. Andromeda is approaching us at about 110 kilometers per second. In roughly 4 to 5 billion years, it will collide with the Milky Way, and the two galaxies will merge into a single, larger system. The approaching collision with Andromeda is interesting because it demonstrates the difference between orbital motion and cosmic expansion. On small scales, within galaxy groups, gravity dominates and objects can move toward each other. The Milky Way and Andromeda are gravitationally bound. They're part of the same structure, orbiting their common center of mass. But on larger scales, cosmic expansion dominates. More distant galaxies are receding from us, carried along by the expansion of space itself. The farther away a galaxy is, the faster it appears to recede. This relationship is described by Hubble's law, and it's what allows us to measure cosmic distances by observing redshift. The Milky Way and Andromeda are part of a small group of galaxies called the Local Group. This group contains about 80 galaxies, most of them small dwarf galaxies that orbit the Milky Way, or Andromeda. The entire Local Group spans about 10 million light-years. The Local Group contains some fascinating objects. The Triangulum Galaxy, also called M33, is the third largest member after the Milky Way and Andromeda. It's a spiral galaxy about 2.7 million light-years away, containing perhaps 40 billion stars. It's gravitationally bound to Andromeda and will likely be part of the eventual Milky Way-Andromeda merger. There are numerous dwarf galaxies in the Local Group. The Magellanic Clouds, visible from the southern hemisphere, are the most prominent. The Large Magellanic Cloud contains about 30 billion stars and orbits the Milky Way at a distance of about 160,000 light-years. It's gravitationally bound to us and will eventually merge with the Milky Way, though probably not for billions of years. Some dwarf galaxies are so faint they're incredibly difficult to detect. Ultra-faint dwarfs might contain only a few thousand stars, making them barely brighter than individual globular clusters. Yet they're definitely galaxies because they're dominated by dark matter. Their stars are moving too fast to be held together by the gravity of visible matter alone. Something invisible is providing additional gravitational pull. Beyond the Local Group, galaxies cluster into larger structures. The Local Group is part of the Virgo supercluster, an enormous collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo supercluster contains thousands of galaxies organized into filaments and sheets, with enormous voids between them. At the heart of the Virgo supercluster is the Virgo cluster itself, a dense concentration of more than 1,000 galaxies, about 54 million light-years from Earth. The Virgo cluster is dominated by giant elliptical galaxies like M87, the galaxy that was famously imaged by the Event Horizon Telescope, showing the shadow of its central supermassive black hole. The Virgo cluster is massive enough that its gravity affects the entire Local Group. We're falling toward it, pulled by the combined gravity of thousands of galaxies. Our motion toward Virgo is superimposed on top of the cosmic expansion, creating a peculiar velocity, a deviation from the smooth expansion flow predicted by Hubble's law. And Alcyoneus, the galaxy we're building toward, has radio jets that span 16.3 million light-years. That's larger than the entire Local Group. If you placed Alcyoneus at the center of our Local Group with its jets aligned properly, those jets would extend well beyond the boundaries of all the galaxies in our cosmic neighborhood. To really grasp this scale, imagine shrinking the Milky Way down to the size of a dinner plate, roughly 25 centimeters across. On this scale, Andromeda would be another dinner plate sitting about 6 meters away, the distance across a small room. The entire Local Group would fit in a space about the size of a large house. Now, on this same scale, Alcyoneus's radio jets would stretch about 40 meters on either side of the galaxy, for a total span of about 80 meters. That's nearly the length of a football field. The visible portion of Alcyoneus, the actual galaxy with its stars, would still be dinner plate sized, but the radio structure extending from it would span the length of a football field. And remember, This structure isn't solid. It's not made of stars or planets. It's made of extremely thin gas, charged particles moving at near light speed, creating bubbles and lobes that emit radio waves. The density of material in these jets is incredibly low, far lower than the best vacuum we can create on Earth. If you were somehow in the middle of one of these jets, you might not even notice. The space would look empty to your eyes. But radio telescopes can detect the faint emissions from the sparse material spread across these vast volumes. The discovery of Alcyoneus raises immediate questions. How did this galaxy create jets this large? What powers them? How long have they been growing? And perhaps most importantly, is Alcyoneus unique? Or are there other galaxies out there with even larger structures that we just haven't found yet? To answer these questions, we need to understand how these radio jets form in the first place. And that means we need to talk about black holes. Not just any black holes, but the supermassive monsters that lurk at the centers of galaxies. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive objects collapse under their own gravity. The most common way this happens is when a massive star reaches the end of its life. Stars are massive balls of hydrogen gas that generate energy through nuclear fusion in their cores. They're in a constant battle between gravity trying to crush them inward and the pressure from fusion pushing outward. As long as the fusion continues, the star remains stable, but fusion requires fuel, and eventually, even the largest stars run out. When a star about 20 or more times the mass of the Sun exhausts its fuel, the fusion stops. The outward pressure disappears, gravity wins. The entire star collapses inward in a fraction of a second. The core compresses to infinite density, or at least to densities where our current physics breaks down and we can't describe what happens. This creates a black hole. But not all black holes form from dying stars. At the centers of most large galaxies, including our own Milky Way, there are supermassive black holes, objects containing millions or billions of times the mass of the Sun. We don't fully understand how these monsters form, but they seem to have grown along with their host galaxies over billions of years, possibly from smaller black holes that merged together and fed on surrounding gas. The supermassive black hole at the center of the Milky Way is called Sagittarius A*, or SGR A* for short. It contains about 4 million solar masses, meaning it has the mass of 4 million stars like our Sun, all compressed into a region about 60 times smaller than the distance from Earth to the Sun. This black hole is relatively quiet right now, not actively feeding on large amounts of material. We know Sagittarius A* exists because we can observe stars orbiting it. Astronomers have tracked individual stars near the galactic center for decades, measuring their positions with incredible precision. These stars orbit extremely fast, some completing full orbits in less than 20 years. By applying Kepler's laws of orbital motion, we can calculate the mass of the object they're orbiting. One star, designated S2, orbits Sagittarius A* with a period of about 16 years. At its closest approach, it reaches speeds of about 7,650 kilometers per second, roughly 2.5% of the speed of light. The orbit is so tight and so fast that we can actually measure relativistic effects. The orbit doesn't quite close on itself the way Newton's laws would predict. Instead, it precesses, rotating slowly over time, exactly as Einstein's general relativity predicts. In 2018, when S2 made its closest approach to the black hole, astronomers measured a gravitational redshift in the star's light. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths. The deeper the well, the greater the shift. The measured redshift matched general relativity's predictions perfectly, providing yet another confirmation that Einstein's theory describes gravity correctly even in extreme environments. but many supermassive black holes are actively feeding, and when they do, they become some of the most energetic objects in the universe. Gas and dust from the surrounding galaxy fall toward the black hole, but they don't fall straight in. They orbit, forming a disk called an accretion disk. As material in this disk spirals closer to the black hole, friction and magnetic fields heat it to millions of degrees. The disk glows brilliantly, often outshining the entire galaxy around it. The physics of accretion disks is complex and not fully understood. We know that magnetic fields play a crucial role. The gas in the disk is a plasma, meaning it's ionized with electrons stripped from atoms. Plasmas interact strongly with magnetic fields. As the plasma swirls around the black hole, it drags magnetic field lines with it, tangling and stretching them. These twisted magnetic fields can extract energy from the rotating black hole through a process called the Blandford-Znajek mechanism, named after the physicists who first described it in 1977. The basic idea is that magnetic field lines threading through the black hole's event horizon can tap into its rotational energy, channeling that energy outward along the poles of the magnetic field. The result is jets, narrow beams of particles and energy shooting outward perpendicular to the accretion disk. These jets are among the most powerful phenomena in the universe. They can extend for millions of light years, carrying enormous amounts of energy away from the black hole and depositing it in the surrounding space. Think of it like water swirling down a drain, but with some of the water being redirected upward in a powerful fountain. Except in this case, the fountain is made of charged particles moving at close to the speed of light, and it extends for millions of light years into space. The particles in these jets are accelerated to tremendous energies. Electrons might have energies millions or billions of times higher than their rest mass energy. These are called relativistic particles because you need Einstein's relativity to describe their behavior. At these energies, particles don't follow the classical rules of physics. They have so much kinetic energy that their effective mass increases dramatically. As these jets plow into the surrounding material, the gas and dust that exists in the space between galaxies, they create shock waves and heat the gas. The heated gas expands, creating enormous lobes or bubbles on either side of the galaxy. These lobes are filled with relativistic particles, electrons and protons moving at speeds approaching light speed, and these particles emit radio waves. The radio waves are produced through a process called synchrotron radiation. When charged particles move through magnetic fields at relativistic speeds, they spiral along the field lines and emit electromagnetic radiation. The exact wavelength depends on the strength of the magnetic field and the energy of the particles, but for the conditions in these radio lobes, most of the emission is in the radio portion of the spectrum. Synchrotron radiation is a well-understood process. We see it in particle accelerators on Earth, where electrons traveling through magnetic fields emit bright synchrotron light. But in cosmic radio lobes, the process operates on a scale trillions of times larger, with particles spread across volumes measuring millions of light years on a side. This is what radio telescopes detect when they observe galaxies like Alcyoneus. They're seeing the glow of these enormous bubbles of hot gas and relativistic particles, structures that can dwarf the visible galaxy by factors of hundreds or even thousands. Now here's what makes Alcyoneus particularly interesting. The jets extend 16.3 million light years, but the galaxy itself is not particularly special in other ways. The host galaxy is a fairly normal elliptical galaxy, sitting about 3 billion light years from Earth. It's large, but not exceptionally so. The supermassive black hole at its center is estimated to contain about 400 million solar masses, which is substantial but not record-breaking. There are many galaxies with larger black holes. M87, for example, has a black hole of about 6.5 billion solar masses, more than 16 times larger than Alcyoneus's black hole. The recently discovered TON 618 quasar, one of the most massive black holes known, might contain 66 billion solar masses, about 160 times larger. So Alcyoneus doesn't have an unusually large black hole. It also doesn't appear to be in an unusual galaxy. The stellar mass of the host galaxy is estimated at about 240 billion solar masses, making it a fairly typical giant elliptical. It's not a particularly active galaxy in terms of star formation. Most of the stars are old, formed billions of years ago, and there's not much gas left to form new stars. So why does Alcyoneus have such enormous jets? What allowed this particular galaxy to create structures so much larger than most others? The research team led by Martijn Uy considered several possibilities. One factor might be the environment. Alcyoneus sits in a relatively sparse region of space, not in a dense galaxy cluster where there would be lots of surrounding gas to push against. In dense environments, jets can be confined or disrupted by interactions with all the material around them. But in a sparse environment, jets can expand freely, growing to enormous sizes without running into obstacles. Think of it like blowing a bubble. If you're in a crowded room full of walls and furniture, your bubble will hit something and pop before it gets very large. But if you're in an open field with nothing around you, that bubble can expand much farther before it encounters resistance. The researchers measured the density of the environment around Alcyoneus using several methods. They looked at how many other galaxies are in the vicinity. They examined the distribution of diffuse X-ray emitting gas that fills the space between galaxies and clusters. They checked whether Alcyoneus is part of a filament in the cosmic web or sits in a void. All the evidence points to Alcyoneus being in a low-density environment. It's not in a cluster. There are some nearby galaxies, but not an unusual number. The ambient gas pressure is low. This sparse environment provides ideal conditions for jets to expand to enormous sizes. Another factor might be time. These jets don't form instantly. They grow over millions or tens of millions of years as the central black hole continues to feed and pump energy into them. If Alcyoneus has had an unusually long period of jet activity without major disruptions, the jets could have grown to exceptional sizes simply because they've had more time to expand. The research team calculated that the jets of Alcyoneus have been active for roughly 1 billion years. That's an enormous amount of time, about 7% of the current age of the universe. During that billion years, the jets have been continuously pumping energy into the surrounding space, pushing the radio lobes farther and farther outward. How do we know the jets have been active for 1 billion years? The calculation involves several factors. First, we can estimate the energy content of the lobes by measuring their radioluminosity and the volume they occupy. This tells us how much energy has been deposited into the lobes over their lifetime. Second, we can estimate the power of the jets by measuring how much energy they're currently depositing. This is harder because we're seeing the galaxy as it was 3 billion years ago, but we can use models based on other similar galaxies to make reasonable estimates. Dividing the total energy by the power gives us the age, the time it would take to build up the observed structure. For Alcyoneus, this calculation suggests roughly 1 billion years of activity, though with substantial uncertainty. The age could be anywhere from a few hundred million to perhaps 2 billion years, depending on various assumptions. There's also the possibility that Alcyoneus had particularly powerful jets at some point in its history. If the central black hole went through a phase of extremely rapid feeding, it could have launched jets with more energy than typical, allowing them to punch farther out into the surrounding space before slowing down. Black holes don't feed at constant rates. They go through cycles. Sometimes a large cloud of gas falls toward the black hole, providing abundant fuel. The black hole feeds voraciously, shining brightly and launching powerful jets. Then the fuel runs out, the black hole goes quiet, and the jets fade. Later, more gas arrives, and the cycle repeats. Evidence for this cyclical behavior comes from observations of radio galaxies at different evolutionary stages. Some show compact jets, suggesting they're young systems where the jets have just started. Others show extended lobes, but no active jets, suggesting the central engine has shut off and the lobes are coasting on momentum. Still others show multiple generations of lobes, indicating several distinct episodes of activity, separated by quiet periods. Alcyoneus might represent a galaxy that has been active for an unusually long continuous period, or it might have experienced several episodes of activity that all contributed to the same pair of expanding lobes. Distinguishing between these scenarios requires detailed modelling and more observations than we currently have. But there's something fascinating about these structures. They're incredibly fragile in a certain sense. The density of material in the radio lobes is so low that even a gentle collision with a cloud of gas or another galaxy could disrupt them. They persist only because the space between galaxies is so empty. There's simply nothing out there to collide with. If Alcyoneus were to pass through a galaxy cluster or encounter a large cloud of intergalactic gas, the jets could be disrupted or bent. We see examples of this in other radio galaxies. Some have jets that curve or kink, where they've encountered denser regions of space. Some have lobes that are asymmetric, larger on one side than the other, because the jet on one side expanded into a lower density region. The symmetry of Alcyoneus's jets suggests the environment on both sides of the galaxy is similar and consistently sparse. The jets have expanded outward through relatively uniform space, encountering only the thin intergalactic medium without any major obstacles. This raises an interesting question. If Alcyoneus has the largest known radio jets, does that mean it will always have the largest jets? Or could the jets continue growing, extending even farther into space over time? The answer depends on whether the central black hole is still active. If it's still feeding and launching jets, then yes, the structures could continue to grow. But at some point, the black hole will exhaust the available fuel. The jets will shut off, and then the lobes will slowly fade over hundreds of millions of years as the particles lose energy and the radio emission dims. We don't know the current state of Alcyoneus's black hole because the galaxy is 3 billion light-years away. The light we see from it left that galaxy 3 billion years ago, when the Earth was very different and the earliest complex life was just beginning to appear in the oceans. The black hole could have shut off 1 billion years ago, and we wouldn't know yet because the light from that shut-off hasn't reached us. This is one of the strange things about astronomy at cosmic scales. We're always looking into the past. Everything we observe happened long ago. The farther away something is, the farther back in time we're seeing. We're not observing the universe as it is now. We're observing a patchwork of different epochs, with nearby objects shown nearly as they are today, and distant objects shown as they were billions of years ago. But Alcyoneus also raises a deeper question. If this galaxy has the largest known jets, but isn't particularly special in other ways, then there should be other galaxies out there with similar or even larger structures. We just haven't found them yet. Remember, Alcyoneus was discovered by analysing LOFAR survey data that covered only a portion of the sky. The full sky is 41,253 square degrees, and the LOFAR surveys have covered a fraction of that in the kind of detail needed to detect these faint extended structures. As more surveys are completed and more data is analysed, astronomers fully expect to find more giant radio galaxies, possibly some even larger than Alcyoneus. In fact, in the same paper where they announced Alcyoneus, the research team identified several other giant radio galaxies with jets spanning 10 million light-years or more. These weren't record breakers, but they showed that extremely large radio galaxies are not as rare as once thought. They're just difficult to find because the emission is so faint and spread out. One of these other giants is designated as J1420 plus 1, 4, 2, 3. Its jets span about 11 million light-years, making it smaller than Alcyoneus but still enormous by any standard. Like Alcyoneus, it sits in a relatively sparse environment at a distance of about 2.6 billion light-years. Its host galaxy and black hole are also fairly typical, reinforcing the idea that environment, rather than exceptional properties of the galaxy or black hole, is the key factor enabling such large jets. Another is J1453 plus 3308, with jets spanning about 11.5 million light-years. This one is even farther away, about 3.3 billion light-years, meaning we're seeing it as it was when the universe was younger. The fact that giant radio galaxies existed several billion years ago tells us that the mechanisms creating them have been operating throughout much of cosmic history. This connects to a broader theme in astronomy. Every time we build a more sensitive instrument or analyze data in a new way, we discover things we couldn't see before. The universe is full of phenomena operating at scales and wavelengths that our eyes and even our traditional telescopes can't detect. Radio astronomy opened a new window on the universe in the mid-20th century. X-ray astronomy did the same. Gamma-ray astronomy, gravitational wave astronomy. Each new window reveals things we didn't know existed, and each discovery reminds us how limited our perspective is. We see only what our instruments allow us to see. There are probably structures and phenomena in the universe that we're completely blind to, simply because we haven't built the right instruments yet, or haven't thought to look in the right way. Alcyoneus is the largest galaxy structure we know of right now, today, with our current technology and observations. But largest known is a very different statement from largest that exists. Somewhere out there in the vastness of space, there might be galaxies with jets spanning 20 million light-years, or 30 million, or even larger. We just don't know. What we do know is that Alcyoneus represents an extreme, a demonstration of just how large cosmic structures can grow when given the right conditions and enough time. And studying these extremes teaches us about the processes that shape all galaxies, including our own. The Milky Way doesn't have jets like Alcyoneus, at least not currently. Our central black hole, Sagittarius A star, is relatively quiet. It's feeding on material, but at a slow trickle, not the massive inflows that would create powerful jets. We see some activity, some X-ray emissions from the region around the black hole, but nothing like the dramatic jets seen in radio galaxies. But this wasn't always the case. Evidence suggests that the Milky Way's central black hole was much more active in the past. Astronomers have found enormous bubbles of gamma-ray, emitting gas extending above and below the galactic disk, structures called the Fermi bubbles, after the Fermi Gamma-Ray Space Telescope that discovered them in 2010. These bubbles span about 50,000 light-years, roughly half the width of the entire galactic disk. They're thought to be the remnants of a burst of activity from Sagittarius A star that occurred a few million years ago. Something fed a large amount of gas into the black hole, possibly a cloud of material that strayed too close. The black hole flared up, launched jets or winds, and created these enormous bubbles that still glow in gamma rays today. The Fermi bubbles were a complete surprise when they were discovered. No one expected to find such large structures associated with the Milky Way's central black hole, but once found, they made sense. They fit with observations of other galaxies showing bubbles and outflows from their central black holes. Our galaxy isn't special. It experiences the same processes as other galaxies, just perhaps less dramatically. The discovery of the Fermi bubbles came from analyzing data from the Fermi telescope, which had been surveying the gamma-ray sky for months. The bubbles are faint, requiring careful background subtraction to see. They're also symmetric, extending above and below the galactic plane in roughly mirror image structures, suggesting they originated from a single event or period of activity at the galactic center. The edges of the bubbles are sharp, indicating they're expanding shockwaves plowing through the surrounding gas. By measuring the temperature and density of gas in the bubbles, astronomers can estimate how much energy was required to create them. The calculations suggest the outburst released about 10 to the 56th ergs of energy, roughly equivalent to the energy of 100,000 supernova. That's an enormous amount of energy, but it's small compared to the energy in the jets of Alcyoneus, which have been operating for 1 billion years. If the Milky Way's black hole had sustained activity on the level of Alcyoneus's black hole, our galaxy might have developed jets extending millions of light years. But Sagittarius, a star, went through only a brief burst of activity before settling back into relative quiescence. This cyclical nature of black hole activity is one reason why the jets of galaxies like Alcyoneus can grow so large. Black holes feed in bursts. They consume the material available, then go quiet until more material falls in. During the feeding phases, they pump energy into the jets. During the quiet phases, the jets coast, continuing to expand outward from momentum, even without fresh energy input. Over billions of years, multiple cycles of activity can build up jets to enormous sizes. Each burst of feeding adds energy to the structure. Each quiet period allows the jets to expand farther. The cumulative effect, given enough time, produces the structures we see in giant radio galaxies. But jets are only one way that black holes affect their host galaxies. The energy output from an active supermassive black hole can have profound effects on star formation throughout the galaxy. When gas collapses to form stars, it needs to be cool and dense. Hot gas has too much pressure and won't collapse under its own gravity. It needs to cool down, radiating away energy until it becomes dense enough for gravity to overcome the pressure and cause collapse. But the energy from black hole jets and winds can heat the gas, making it expand and preventing it from collapsing. This is called feedback, and it's thought to be one of the main mechanisms regulating star formation in large galaxies. Without feedback, simulations suggest that galaxies would convert far more of their gas into stars than we actually observe. The central black hole acts as a thermostat, preventing runaway star formation by injecting energy into the gas whenever it starts to accumulate and cool. This creates a self-regulating cycle. Gas cools and accumulates toward the center of the galaxy. Some of it feeds the black hole, causing it to become active. The active black hole launches jets and winds that heat the gas, preventing further infall. Star formation shuts down. The black hole goes quiet. Gas begins to cool and accumulate again. The cycle repeats. This feedback process helps explain an observed relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. More massive galaxies have more massive black holes, but not in a random way. There's a tight correlation. Galaxies with higher stellar velocity dispersions, a measure of how fast stars are moving randomly in the galaxy, have more massive black holes. This correlation, called the M-sigma relation, suggests that black holes and galaxies grow together in a linked fashion. The black hole's feedback affects how the galaxy forms stars. The galaxy's mass determines how much gas can fall toward the black hole. They co-evolve, each influencing the other. In the case of Alcyoneus, the jets extending 16 million light-years are depositing enormous amounts of energy into the space around the galaxy. This energy affects not just the host galaxy, but potentially neighboring galaxies as well. If there are other galaxies within those radiolobes, the hot gas and relativistic particles could heat their gas reservoirs, affecting their star formation rates. This creates a kind of cosmic ecology where galaxies influence each other across millions of light years. A giant radio galaxy like Alcyoneus doesn't exist in isolation. It's connected to its environment through these vast energy outflows, shaping the evolution of surrounding space. And here's something that makes this even more interesting. The jets of Alcyoneus and similar galaxies don't just push gas around. They also carry magnetic fields and can seed the space between galaxies with these fields. Magnetic fields are essentially invisible structures created by moving electric charges. They permeate much of the universe, threading through galaxies, galaxy clusters, and even the voids between clusters. We detect them by observing how they affect other phenomena, like the polarization of light or the motion of charged particles. The jets of radio galaxies are one mechanism for spreading magnetic fields into the intergalactic medium. The fields are carried outward with the jets and deposited in the lobes. Over time, these fields can diffuse into the surrounding space, creating large-scale magnetic structures that persist long after the jets shut off. Measuring these magnetic fields is challenging. The most common method involves observing the polarization of synchrotron radiation. When relativistic electrons emit synchrotron radiation in a magnetic field, that radiation is partially polarized, with the electric field vector aligned perpendicular to the magnetic field direction. By measuring the polarization angle of radio emission from different parts of the jets and lobes, we can map the magnetic field structure. For Alcyoneus, such measurements show that the magnetic fields are generally aligned along the jets, as expected if the fields are being carried outward by the flow of material. The strength of these fields can also be estimated. Radio observations combined with X-ray observations of the same regions allow us to separate the energy in magnetic fields from the energy in relativistic particles. For Alcyoneus's lobes, the magnetic field strength is estimated at a few microgauss, about 1,000,000 times weaker than Earth's magnetic field at the surface. That might sound incredibly weak, but remember these fields pervade volumes millions of light years across. The total energy contained in the magnetic fields of Alcyoneus's lobes is enormous, perhaps comparable to the energy of 1 billion supernova. These magnetic fields might play a role in cosmic ray propagation, affecting how high-energy particles travel through space. They might influence the formation of structure in the universe, affecting how gas flows and where galaxies form. This is an active area of research, and discoveries like Alcyoneus provide important data points for understanding these processes. The study of giant radio galaxies is also connected to one of the biggest mysteries in cosmology, the nature of the intergalactic medium itself. Space between galaxies isn't completely empty. There's gas out there, extremely tenuous, but present nonetheless. This gas is part of the cosmic web, the large-scale structure of the universe made up of filaments and sheets of dark matter and ordinary matter connecting galaxy clusters. But measuring the density and properties of this intergalactic gas is difficult. It's too diffuse to see directly in most wavelengths. Astronomers have to use indirect methods, like observing how the gas absorbs light from distant quasars, or how it affects the cosmic microwave background. Quasar absorption lines provide some of our best information about the intergalactic medium. When we observe distant quasars, bright active galaxies whose light has traveled billions of light years to reach us, we see absorption lines in their spectra. These lines are created when light passes through clouds of gas between us and the quasar. Each cloud absorbs light at specific wavelengths corresponding to the elements it contains. Hydrogen is the most common, but we also see absorption from heavier elements. By studying these absorption lines, we can map out the distribution of gas along the line of sight to the quasar. What we find is that gas is indeed distributed throughout space, but not uniformly. It clusters along filaments exactly as the cosmic web model predicts. Dense filaments contain more gas, void regions contain less, and galaxies tend to form where filaments intersect, where gas is densest. The jets from galaxies like Alcyoneus provide another way to probe the intergalactic medium. As the jets expand, they push against the surrounding gas. The resistance they encounter affects how fast they can grow and what shape they take. By studying the morphology and dynamics of the jets, astronomers can infer properties of the gas they're interacting with. In the case of Alcyoneus, the fact that the jets have grown so large suggests the intergalactic medium in that region is particularly sparse. If there were more gas, the jets would have encountered more resistance and wouldn't have expanded as far. This gives us information about the density of material in that region of space 3 billion years ago. Information that's difficult to obtain any other way. By combining observations of many giant radio galaxies in different environments and at different distances, we can build up a statistical picture of how the intergalactic medium has evolved over cosmic time. We can see whether the average density has changed, whether the distribution has become more or less clumpy, and how this connects to the formation and evolution of galaxies. This is part of a larger effort to understand the baryon cycle, how ordinary matter moves between different phases and locations over cosmic history. Baryons, the protons and neutrons that make up atoms, cycle through many stages. They start as diffuse gas in the intergalactic medium. They fall into galaxies where some fraction condenses to form stars. Stars eventually return much of their material to the interstellar medium through stellar winds and supernovae. Some of that material is launched back into the intergalactic medium by galactic winds and jets. And the cycle continues. Understanding this cycle is crucial for understanding galaxy evolution. Galaxies aren't closed systems. They're constantly exchanging material with their surroundings. The rate at which gas flows in affects star formation. The rate at which gas is expelled affects how long a galaxy can sustain star formation. Giant radio galaxies like Alcyoneus play a role in this cycle by heating and redistributing gas on enormous scales. The energy from their jets can prevent gas from cooling and falling into galaxies, reducing star formation rates across large regions. And this brings us to one of the most profound aspects of Alcyoneus and galaxies like it. They're not just objects to study, they're tools for studying the universe itself. They're probes that extend across cosmic distances, sampling conditions in regions we could never visit, and revealing the structure and evolution of the cosmos on the largest scales. When we look at Alcyoneus, we're not just seeing a galaxy. We're seeing a natural experiment in gravity, magnetism, plasma physics, and cosmic evolution that has been running for 1 billion years across 16 million light-years of space. We're seeing the imprint of a supermassive black hole on the structure of the universe. We're seeing energy and matter transformed and transported on scales that challenge our imagination. And we're reminded of just how dynamic the universe is. Galaxies aren't static. They're evolving, changing, interacting with each other and their environments in complex ways. Over cosmic timescales, they merge and transform. They trigger star formation and shut it down. They launch jets that reshape space around them. They grow and fade and eventually die, leaving behind remnants that will become part of future generations of galaxies. Let's zoom out even further and think about what Alcyoneus means in the broader context of cosmic structure. We've talked about galaxies and galaxy groups and galaxy clusters. But these are just the smallest units of large-scale structure in the universe. When you map the positions of millions of galaxies across large volumes of space, a pattern emerges. Galaxies aren't randomly scattered. They cluster along filaments and sheets, creating a web-like structure on the largest scales. These filaments stretch for hundreds of millions of light-years, connecting massive galaxy clusters and defining enormous voids with very few galaxies. This is the cosmic web, the largest scale structure in the universe. It formed in the first few 100 million years after the Big Bang from tiny density variations in the early universe. Regions that were slightly denser than average pulled in more matter through gravity, becoming denser still. Regions that were slightly less dense lost matter to their neighbors, becoming voids. Over billions of years, this process created the structure we see today. Dense nodes where galaxy clusters sit, filaments connecting the nodes, and vast, empty voids between them. If you could view the universe from an enormous distance, you'd see this cosmic web stretching across billions of light years, a foam-like structure of walls and voids. The cosmic web wasn't observed directly until relatively recently. In the 1980s, astronomers began conducting redshift surveys, measuring the distances to thousands of galaxies and plotting their three-dimensional positions. When Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics published their results in 1989, the astronomy community was stunned. The galaxies weren't distributed uniformly or even in simple clusters. They formed sheets and filaments with enormous voids between them. One structure, which they called the Great Wall, stretched across 500 million light-years of space. It was a sheet of galaxies, thousands of them, arranged in a thin structure that dwarfed anything previously imagined. Since then, larger and more comprehensive surveys have revealed the cosmic web in ever greater detail. The Sloan Digital Sky Survey, which began in 2000, has mapped the positions of millions of galaxies. The data shows filaments extending across billions of light years, connecting galaxy clusters like beads on cosmic strings. Alcyoneus exists within this cosmic web. The galaxy sits in a relatively sparse region, not in a dense cluster, but not in a complete void either. It's likely part of a filament, though at 3 billion light-years away and with the limited data we have, it's difficult to map its exact position in the cosmic web with certainty. But what's fascinating is that the jets of Alcyoneus could span multiple nodes in the web. If you imagine the cosmic web as a sponge, with dense regions where the sponge material is, and voids where the holes are, Alcyoneus's jets could potentially stretch from one part of the sponge to another, crossing through a void in between. This means the jets are sampling very different environments. Near the galaxy, they're pushing through gas that's relatively dense by intergalactic standards, part of the filament where the galaxy sits. Farther out, they might be expanding into void regions where there's almost nothing, allowing them to grow even larger. The relationship between the cosmic web and radio galaxy jets is an active area of research. Some studies have found that the largest radio galaxies tend to be in less dense environments, supporting the idea that sparse surroundings allow jets to expand farther. Other studies have found that alignment matters too. Jets aligned along filaments might be able to expand farther than jets perpendicular to filaments. The cosmic web itself is shaped by dark matter, the mysterious substance that makes up about 85% of all matter in the universe but doesn't emit or absorb light. We can't see dark matter directly, but we can map it by observing how its gravity affects visible matter. Computer simulations of cosmic structure formation show that dark matter forms the scaffolding of the cosmic web first. Dark matter doesn't interact with light or normal matter except through gravity, so it can collapse into dense structures without being slowed by pressure or friction. These dark matter structures then pull in normal matter through gravity, and galaxies form where the normal matter becomes dense enough. The filaments and sheets of the cosmic web are composed mostly of dark matter, with normal matter making up only about 15% of the total mass. Most of the normal matter is in the form of hot gas that fills the space between galaxies, too diffuse and too hot to form stars, but dense enough to affect observations in various ways. One way we detect this hot intergalactic gas is through its interaction with the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. When cosmic microwave background photons pass through hot gas, some of them scatter off electrons in the gas. This scattering slightly distorts the spectrum of the cosmic microwave background in a way we can detect. This effect, called the Sunyaev-Zeldovich effect after the physicists who predicted it in 1969, allows us to map the distribution of hot gas throughout the universe. We see it concentrated in galaxy clusters, where temperatures reach tens of millions of degrees. We see it along filaments connecting clusters, and we see it absent from void regions, confirming that voids are truly empty. Alcyoneus's jets are interacting with this hot, intergalactic gas. As the jets push outward, they're heating the gas even further, creating shock waves and turbulence. The energy deposited by the jets contributes to the thermal budget of the intergalactic medium, affecting its temperature and pressure. On cosmic scales, the feedback from radio galaxies might be an important factor in determining how gas cools and flows through the cosmic web. If jets heat the gas too much, it won't be able to cool and fall into galaxies to form stars. This could reduce the overall star formation rate in the universe, shaping the population of galaxies we see. The study of the cosmic web is one of the frontiers of cosmology. By mapping where galaxies are and how they cluster, astronomers can test our understanding of gravity, dark matter, and the evolution of the universe. The cosmic web is shaped by the same physical processes that operate everywhere, from the formation of planets to the collision of galaxy clusters. And here's something profound. The cosmic web we see today is a snapshot of a structure that's been evolving for nearly 14 billion years. When we look at nearby galaxy clusters, we're seeing the web as it exists today, or nearly so. When we look at distant structures billions of light years away, we're seeing the web as it existed billions of years ago, when it was younger and less evolved. By comparing the cosmic web at different epochs, we can watch structure grow over time. We can see how filaments have become more defined, how clusters have grown more massive, how voids have become emptier as matter drains out of them toward the filaments. This is possible because of the finite speed of light. Light takes time to travel, so looking farther in space is the same as looking back in time. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A galaxy 5 billion light-years away appears as it was 5 billion years ago. By observing galaxies at many different distances, we're effectively creating a time-lapse movie of cosmic evolution. Alcyoneus, at 3 billion light-years away, shows us what giant radio galaxies were like 3 billion years ago. If we find similar objects at greater distances, we can see whether such structures were common in earlier epochs, or whether they've become more or less common over time. Early results suggest that giant radio galaxies existed throughout much of cosmic history. We see them at redshifts, corresponding to when the universe was only a few billion years old. We see them in the middle epochs when the universe was half its current age, and we see them today. This suggests that the mechanisms creating these giants, powerful black holes in sparse environments with long periods of activity, have been operating for most of cosmic history. Let's talk about how we actually observe something 3 billion light-years away and spanning 16 million light-years. What does the process of discovery look like? And what challenges do astronomers face when trying to study these objects? Radio astronomy is different from optical astronomy in fundamental ways. When you look through an optical telescope, you're collecting light that your eyes could detect if they were sensitive enough. The telescope just gathers more light than your eye can, making faint objects visible and revealing details too small for your eye to resolve. Radio telescopes work on the same basic principle, but with a major difference. Radio waves have much longer wavelengths than visible light. Wavelengths of meters or even kilometers, compared to the tiny fractions of a millimeter for visible light. This has consequences for telescope design. The resolution of a telescope, its ability to distinguish fine details, depends on the ratio of the telescope's size to the wavelength of light it's detecting. This ratio is measured in terms of the number of wavelengths that fit across the telescope's aperture. For visible light with wavelengths around 500 nanometers, a telescope 1 meter across spans about 2 million wavelengths. This provides excellent resolution. But for radio waves with wavelengths of, say, 2 meters, that same 1 meter telescope spans only half a wavelength. The resolution would be terrible. You couldn't distinguish any details. To achieve the same resolution at radio wavelengths as a 1 meter optical telescope achieves at visible wavelengths, you'd need a radio telescope 4 million meters across. That's 4,000 kilometers. Obviously, you can't build a single telescope 4,000 kilometers across, but you can simulate one using interferometry. This is the technique that makes modern radio astronomy possible, and it's worth understanding in some detail because it's fundamental to discoveries like Alcyoneus. Interferometry works by combining signals from multiple separate telescopes. Imagine you have 2 radio dishes separated by some distance. A radio wave from a distant source arrives at both dishes, but because they're in different locations, the wave arrives at slightly different times. The time difference depends on the direction to the source and the separation between the dishes. If the source is directly overhead and the dishes are east-west of each other, the waves arrive simultaneously. If the source is to the east, the eastern dish receives the wave first. If it's to the west, the western dish receives it first. By measuring these time differences very precisely and combining the signals from both dishes, you can determine the direction to the source much more accurately than you could with either dish alone. And by using many dishes in different configurations, you can build up a detailed image of the radio sky. The effective resolution of an interferometric array is determined by the maximum separation between any 2 dishes, not by the size of the individual dishes. So if you have dishes separated by 1,000 kilometers, your resolution is as good as a single dish 1,000 kilometers across, even if each individual dish is only 25 meters across. But there's a catch. To make this work, you need to know the position of each dish with extraordinary precision. You need to know exactly when signals arrive at each dish. And you need to combine the signals in just the right way to extract the information about the source. This requires atomic clocks synchronized to within nanoseconds, GPS positioning accurate to millimeters, and powerful computers to process the data. The technique was developed in the 1950s and 60s, but it's only in recent decades that the technology has matured to the point where we can build large interferometric arrays covering continents. LOFAR, the low-frequency array that discovered Alcyoneus, is one of the most sophisticated interferometric arrays ever built. It consists of thousands of individual antennas spread across Europe, with concentrations in the Netherlands, Germany, France, Sweden, Poland, and other countries. The design of LOFAR is elegant in its simplicity. The individual antennas are just metal wires or tiles arranged in specific patterns. There are 2 types of antennas: low-band antennas, which look like simple inverted V-shaped wire dipoles, detect radio waves with wavelengths between 10 and 90 meters. High-band antennas, which look like Christmas trees made of metal tiles, detect waves with wavelengths between 1.2 and 3 meters. These antennas have no moving parts. They don't point at the sky mechanically. Instead, the telescope steers electronically by combining signals from different antennas with computer-controlled delays. Want to look at a different part of the sky? Just change the delays in the signal processing. The antennas themselves don't move. This makes LOFAR incredibly flexible. It can observe multiple targets simultaneously by processing the data in different ways. It can create wide-field images covering large portions of the sky, and it can operate continuously, building up sensitivity over long observation periods. The antennas are arranged in stations. Each station contains dozens or hundreds of individual antennas clustered in a field. The signals from all antennas in a station are combined locally to create a single data stream. Then the data streams from different stations are combined to create the final images. LOFAR has a core in the Netherlands where many stations are concentrated in a relatively small area. This provides good sensitivity to extended structures. It also has remote stations spread across Europe. The longest baseline, the maximum separation between any two stations, is about 2,000 kilometers. This provides high resolution, the ability to see fine details. For a survey like the one that discovered Alcyoneus, LOFAR observes a region of the sky for several hours. The data from all the stations is recorded and sent to processing centers, where it's combined using sophisticated algorithms. A single observation can generate hundreds of terabytes of raw data. Processing this data is computationally intensive. The raw data needs to be calibrated, corrected for various effects, and then combined to create images. The calibration is particularly challenging because the signals from the stations have to be aligned to within nanoseconds, despite having traveled different paths through the atmosphere and through the electronics. The atmosphere itself introduces delays. Radio waves travel slightly slower through ionized gas than through vacuum. The Earth's ionosphere, a layer of ionized gas between about 60 and 1,000 kilometers altitude, contains free electrons that affect radio waves. The number of electrons along the path from source to antenna changes with time of day, solar activity, and even local weather. LOFAR operates at low frequencies where these ionospheric effects are strongest. The delay introduced by the ionosphere can be larger than the delay from the geometry of the array. This means you can't just point the telescope and get good images. You have to constantly monitor the ionosphere and correct for its effects in the data processing. The techniques for doing this are sophisticated. LOFAR uses bright radio sources as calibrators. It observes these sources and measures how the ionosphere is affecting them. Then it uses this information to correct the observations of other sources in the same region of sky. The images that come out of this processing show the radio sky at the frequencies LOFAR observes. What you see are sources of radio emission, galaxies with active black holes, supernova remnants, pulsars, and other radio bright objects. But the images don't look like optical images. They're maps of radio intensity, showing where radio emission is strongest. For an extended source like Alcyoneus, the radio emission is spread out over a huge area on the sky. Remember, the jets span 16 million light-years at a distance of 3 billion light-years. To figure out how large this appears on the sky, we need to do a bit of geometry. At a distance of 3 billion light-years, the angular size of an object depends on the cosmological model we're using, but roughly speaking, 1 million light-years corresponds to about 0.2 degrees on the sky. So 16 million light-years spans about 3.2 degrees, roughly 6 times the width of the full moon. This is actually quite large in astronomical terms. Most radio sources are much smaller, appearing as points or small fuzzy patches. A source spanning 3 degrees is enormous, and it presents special challenges for observation. When you have a very extended source, the radio emission is spread out over a large area. The total flux, the total amount of radio energy we receive, might be substantial, but the surface brightness, the flux per unit area on the sky, is low. Extended sources are faint in terms of surface brightness, even if they're bright in terms of total flux. This is why giant radio galaxies are hard to find. If you use a radio telescope designed to study compact sources, you might miss the extended emission entirely. The extended structure is too faint to stand out against the background noise. You need a telescope specifically designed to detect faint extended emission. LOFAR excels at this because its core stations provide excellent sensitivity to large-scale structures. The close spacing of stations in the core means the array is sensitive to emissions spread over large angular scales. Other radio telescopes, with only long baselines, would miss this diffuse emission entirely. For Alcyoneus, the discovery came from careful analysis of survey data. Martin Oey was specifically looking for giant radio galaxies, so he developed techniques to identify them in the LOFAR data. The process starts by identifying all the radio sources in a region of the sky. LOFAR survey data covers thousands of square degrees, containing hundreds of thousands of radio sources. Most are compact, concentrated in small regions, but some show extended emission. OEI's technique involved looking for sources with emission extending far from a central galaxy. He used algorithms that could trace out faint, extended structures even when they were just barely above the noise level. This is a bit like trying to see a very faint, very large cloud in a twilight sky. Your eye might miss it because it's so diffuse, but if you look carefully and know what to look for, you can trace its outline. When he found Alcyoneus, the extended emission was clear but subtle. The lobes appeared as diffuse patches of radio emission on either side of a central galaxy. The key was recognizing that these patches were connected to the same source. Radio galaxies with jets typically show a characteristic morphology. There's a bright central region where the galaxy itself is located. Then there are jets extending outward from the nucleus. Finally, there are lobes at the ends of the jets, where the outflowing material terminates and creates expanding bubbles. In the most powerful radio galaxies, called Phaneroff-Rayleigh class, two sources after the astronomers who first classified them, the lobes are brightest at their outer edges. This creates a distinctive pattern, bright hot spots at the ends of the jets where the material is crashing into the intergalactic medium. Alcyoneus shows this classic FR2 morphology, but on a scale far larger than typical. The central galaxy is visible. The jets extend outward, though they're quite faint, and the lobes show bright hotspots at their outer edges, exactly where you'd expect if powerful jets are driving into the surrounding space. To confirm the discovery, Oey and his team needed to verify that all this emission was coming from a single source at a single distance. This meant measuring the redshift of the central galaxy. Every galaxy has a characteristic spectrum, a pattern of bright and dark lines corresponding to elements in the galaxy's stars and gas. These spectral lines have specific wavelengths when measured in a laboratory on Earth. But when you observe a distant galaxy, the wavelengths are shifted to longer values because the expansion of the universe stretches the light as it travels. This is redshift, denoted by the letter Z. It's defined as the fractional change in wavelength. V equals open parenthesis, observed wavelength minus rest wavelength, close parenthesis, over rest wavelength. A galaxy with Z equals 0.1 has its light stretched by 10%. A galaxy with Z equals 1 has its light stretched by 100%, meaning wavelengths are doubled. A galaxy with Z equals 2 has wavelengths tripled. The amount of redshift tells you how far away the galaxy is, though the relationship isn't straightforward because the universe's expansion rate has changed over time. You need to use a cosmological model that accounts for the expansion history to convert redshift to distance. Alcyoneus has a redshift of about Z equals 0.247. This was measured using optical spectroscopy, where light from the central galaxy was split into its component wavelengths, and the positions of spectral lines were measured. The redshift corresponds to a distance of roughly 3 billion light-years using standard cosmological models. This distance measurement is crucial. It allows you to convert the angular size of the jets, how large they appear on the sky, into their actual physical size. The jets span about 3.2 degrees at a redshift of 0.247. Plugging these numbers into the cosmological equations gives a physical size of approximately 16.3 million light-years. There's uncertainty in this measurement, of course. The redshift has some uncertainty, perhaps plus or minus 0.001 or so. The cosmological model has parameters that aren't known perfectly. The edges of the jets are diffuse, so defining exactly where they end involves some judgment. Taking all these factors into account, the size measurement probably has an uncertainty of around 5 to 10%, meaning the true size could be anywhere from about 15 to 17 million light-years. Still enormous by any measure, and still the largest confirmed radio galaxy structure known. But measuring size is only the first step. OEI and his colleagues wanted to understand the physical properties of the jets and lobes. How much energy do they contain? How powerful are the jets? How long have they been active? To answer these questions, you need to measure the radioluminosity, the total amount of radio energy being emitted. You also need to estimate the volume of the lobes and the density of relativistic particles within them. And ideally, you'd like to measure the magnetic field strength. Radioluminosity can be measured directly from the observations. You measure the flux density, the amount of radio energy received per unit area of your telescope per unit frequency. Then, you convert this to luminosity using the distance to the source. The farther away something is, the more luminous it must be to produce the same observed flux. For Alcyoneus, the total radioluminosity is about 5 times 10 to the power of 41 ergs per second, or about 5 times 10 to the power of 34 watts. That's about 10 million times the total luminosity of the Sun across all wavelengths. But remember, this radio emission is coming from a structure 16 million light-years across, so the energy density is actually quite low. Estimating the volume is straightforward geometry once you know the size. The lobes are roughly ellipsoidal, so you can approximate their volume using the formula for an ellipsoid. For Alcyoneus, each lobe has a volume of roughly 10 to the power of 75 cubic centimeters. That's a fantastically large number, but space is mostly empty even in these lobes. The density of relativistic particles is harder to estimate. You can infer it from the radio emission, but you need to know the magnetic field strength to do this accurately. The radio emission comes from synchrotron radiation, and the amount of emission depends on both the number of particles and the strength of the magnetic field. There are techniques to estimate both quantities, simultaneously using radio observations at multiple frequencies, combined with X-ray observations if available. The idea is that the same relativistic electrons that emit radio waves through synchrotron radiation also emit X-rays through a process called inverse Compton scattering. In inverse Compton scattering, relativistic electrons collide with photons and boost them to higher energies. If you can measure both the synchrotron radio emission and the inverse Compton X-ray emission from the same region, you can determine both the particle density and the magnetic field strength separately. For Alcyoneus, X-ray observations haven't been published yet, so the magnetic field strength has to be estimated using other methods. One common approach is to assume equipartition, the idea that energy is roughly equally divided between particles and magnetic fields. This is a reasonable assumption for many astrophysical plasmas, though it's not always accurate. Using equipartition arguments, the magnetic field in Alcyoneus's lobes is estimated at a few microgauss. The particle density is estimated at about 10 to the power of -5 electrons per cubic centimeter. For comparison, the best laboratory vacuums on Earth contain about 10 to the 6th particles per cubic centimeter. The lobes of Alcyoneus are vacuum by terrestrial standards, but they contain enough particles spread over such enormous volumes that their total energy content is substantial. The total energy in the lobes, counting both particles and magnetic fields, is estimated at about 10 to the power of 60 ergs. That's roughly the amount of energy the Sun will emit over its entire 10 billion year lifetime, all contained in these diffuse bubbles of plasma and magnetic fields. Where did this energy come from? From the black hole, through the jets. If the jets have been operating for 1 billion years, then the average power they've been pumping into the lobes is about 10 to the power of 42 ergs per second. That's the total energy divided by the time, and it represents the sustained power output from the black hole's accretion system. This is an enormous power output, but it's not unprecedented. The most powerful radio galaxies, the ones classified as Fanaroff-Rayleigh Class II sources, typically have jet powers in the range of 10 to the power of 43 to 10 to the power of 45 ergs per second. Alcyoneus is at the lower end of this range, which makes sense. If the jets were extremely powerful, they probably wouldn't have expanded to such large sizes. They would have blown through the surrounding medium more violently, creating different structures. The fact that Alcyoneus has relatively moderate jet power but enormous size supports the idea that environment and time are the key factors. The jets don't need to be extraordinarily powerful, they just need to operate steadily for a long time in a sparse environment where they can expand freely. So what's next for Alcyoneus? Now that it's been discovered, what can we learn from studying it further? And how does this discovery fit into the bigger picture of understanding galaxy evolution and cosmic structure? One immediate question is whether Alcyoneus is unique or just the first of many similar galaxies waiting to be found. As I mentioned earlier, the research team that discovered Alcyoneus also identified several other giant radio galaxies in the same dataset, galaxies with jets spanning 10 million light-years or more. This suggests that extremely large radio galaxies are not freakishly rare one-of-a-kind objects. They're just at the extreme end of a distribution. If you survey enough of the sky with sufficient sensitivity, you'll find them. And as surveys continue and cover more of the sky, we should expect to find more. The LOFAR 2-meter sky survey, or LOTSS for short, is an ongoing project to map the entire northern sky at radio wavelengths. When complete, it will cover about 20,000 square degrees, nearly half the entire sky. The data will contain millions of radio sources, and hidden among them will certainly be more giant radio galaxies. Early releases from LOTSS have already revealed several new giants. As of 2024, astronomers have identified roughly 50 radio galaxies with lobes extending more than 5 million light-years. About a dozen of these exceed 10 million light-years. And Alcyoneus remains the largest at 16.3 million light-years, though that record could fall at any time as more data is analysed. In fact, there are good reasons to expect larger structures might exist. LOFAR is sensitive, but it's not infinitely sensitive. If there's a radio galaxy even more extended than Alcyoneus, but slightly fainter, LOFAR might miss it. The emission could be too diffuse to detect against the background noise. Future radio telescopes will be even more sensitive. The Square Kilometre Array, or SKA, currently under construction in South Africa and Australia, will be the most powerful radio telescope ever built when it's completed. The SKA is a truly international project involving countries from around the world. It's being built in 2 phases. SKA-1, the first phase, will consist of thousands of dish antennas in South Africa and hundreds of thousands of low-frequency antennas in Australia. SKA-2, the second phase planned for the 2030s, will expand the array even further. When complete, the SKA will have a collecting area of about 1 square kilometre, hence the name. That's about 50 times more collecting area than any current radio telescope. More collecting area means more sensitivity, the ability to detect fainter sources. The SKA will be able to detect radio galaxies to much greater distances than LOFAR. It will find objects that are too distant or too faint for current telescopes. And crucially, it will be able to detect very extended, very low surface brightness structures that might be invisible to current instruments. When the SKA begins operations, probably in the early 2030s, It might discover radio galaxies even larger than Alcyoneus, or it might reveal that 16 million light-years represents a natural upper limit, a maximum size that jets can reach given the properties of the universe and the timescales involved. What determines this limit? There are several factors to consider. First, there's the age of the universe itself. The universe is about 13.8 billion years old. Radio jets typically last for tens of millions to hundreds of millions of years before the central black hole runs out of fuel and shuts off. In rare cases, they might last 1 billion years or more, as Alcyoneus apparently has. But even 1 billion years is less than 10% of the age of the universe. And during that time, the jets are expanding at some rate determined by the power of the outflow and the resistance of the surrounding medium. There's a limit to how far jets can expand before either the black hole shuts off or the expansion slows to a crawl. Second, there's the density of the intergalactic medium. Even in the most empty regions of space, there's some gas. As jets expand into this gas, they have to push it aside, and this takes energy. The farther the jets extend, the more gas they've had to displace, and the more energy that requires. At some point, the jets might expand so far that they've used up all their energy just pushing gas aside. They can't expand any farther without additional energy input from the black hole. If the black hole shuts off, the expansion stops. Third, there's the structure of the cosmic web. Jets might be able to expand farther along filaments than across them. Filaments have gas distributed along their length, but voids between filaments are nearly empty. A jet aligned with a void might be able to expand into truly empty space, reaching sizes larger than a jet in a typical filament environment. The combination of these factors probably sets a practical limit on jet size. Based on current understanding, jets extending more than 20 to 30 million light-years would be extremely rare. They would require a perfect combination of circumstances: a powerful black hole that remains active for a very long time, an unusually sparse environment, and perhaps favorable alignment with large-scale structure. Alcyoneus, at 16.3 million light-years, might be close to this theoretical maximum, or there might be even larger structures waiting to be found. Only more observations will tell. Another question is what we can learn about the life cycle of radio jets by studying Alcyoneus and similar galaxies. Jets are not static. They evolve over time. They turn on and off as the central black hole goes through cycles of feeding and quiescence. They expand, fade, and eventually dissipate. The evolution of radio jets is thought to follow a predictable pattern. When a black hole first becomes active and starts launching jets, the jets are compact and bright. They're ploughing into the dense gas near the galaxy, creating hotspots where the jet material shocks and heats the surrounding medium. This is the compact symmetric object phase. The jets are young, perhaps only a few thousand years old, and they're still confined to the inner regions of the galaxy, extending maybe a few thousand light-years at most. As the jets continue to push outward, they enter the Fanaroff-Riley phase, named after the classification scheme I mentioned earlier. FR1 sources have jets that fade as they extend outward. FR2 sources have jets that remain collimated and terminate in bright hotspots at large distances. Alcyoneus is an FR2 source with bright hotspots at the ends of its jets. Over millions of years, FR2 jets expand outward, creating the large lobes we observe. As long as the central black hole remains active, the jets continue to pump energy into the lobes, maintaining their brightness and driving further expansion. But eventually, the black hole runs out of fuel. The accretion rate drops, the jets weaken, and eventually shut off completely. When this happens, the lobes begin to fade. The relativistic particles gradually lose energy through synchrotron radiation and other processes, The radio emission dims over timescales of tens to hundreds of millions of years. These fading sources are called remnant radio galaxies or radio phoenixes. They're difficult to study because they're faint, but they're important for understanding the complete life cycle of radio jets. A few dozen remnant radio galaxies have been identified, showing diffuse, low surface brightness emission with no obvious connection to active jets. Alcyoneus appears to still be in the active phase. The jets show bright hotspots, suggesting ongoing activity. But without more detailed observations, it's hard to say whether the black hole is currently feeding vigorously or whether we're seeing the afterglow of activity that shut off some time ago. Remember, we're seeing Alcyoneus as it was 3 billion years ago. The black hole's current state is unknown. It might still be active. It might have shut off millions or even billions of years ago. We won't know until the light from those more recent epochs reaches us, which won't be for billions of years. By studying jets at different stages of evolution and in different environments, astronomers can build models of how jets behave over millions and billions of years. Alcyoneus represents one data point in this effort, an example of a jet that has grown to exceptional size over an extended period of time. Comparing Alcyoneus to other radio galaxies with smaller jets can reveal what factors are most important for jet growth. Is it the power of the jet, the density of the environment, the time the jet has been active, the alignment with cosmic structure? Statistical studies of large samples of radio galaxies are beginning to answer these questions. Early results suggest that all these factors matter, but environment seems to be particularly important. Jets in dense clusters rarely grow beyond a few 100,000 light-years. Jets in moderate density environments might reach 1 million light-years. But jets in very sparse environments can grow to multi-million light-year scales. The power of the jets also matters, but perhaps not in the way you'd expect. Very powerful jets might actually produce smaller structures because they plow through the surrounding medium so violently that they create turbulence and instabilities that disrupt the jets before they can expand far. Moderate power jets, like those of Alcyoneus, might be more stable and able to expand farther given enough time. It's a bit like the difference between a fast, turbulent river and a slow, steady stream. The fast river might seem more powerful, but the slow stream can travel farther before dissipating. Time is probably the most important factor for creating the very largest jets. You need sustained activity over hundreds of millions or even billions of years. Most radio galaxies have multiple episodes of activity separated by quiet periods. Each episode builds up jets, but then they fade during the quiet periods. To create jets as large as Alcyoneus, you probably need either one very long episode of activity or multiple episodes that all contribute to the same growing structure. There's also the question of what happens to these enormous structures over even longer timescales. The jets of Alcyoneus have been growing for roughly 1 billion years, but the universe is nearly 14 billion years old. What will happen to these jets over the next several billion years? If the central black hole has shut off, the jets will stop being fed new energy. The lobes will begin to fade as the relativistic particles lose energy and the radio emission dims. The timescale for this fading depends on several factors. Relativistic electrons lose energy primarily through synchrotron radiation and inverse Compton scattering. The rate of energy loss depends on the energy of the electrons, the magnetic field strength, and the density of photons they can scatter. For the conditions in Alcyoneus's lobes, electrons with energies corresponding to the observed radio emission would lose half their energy in somewhere between 10 million and 100 million years. This means the lobes would fade significantly on timescales of tens of millions of years after the jets shut off. But the lobes wouldn't disappear immediately. Some residual emission would persist for much longer. And the structure of the lobes, the bubbles of hot gas and magnetic fields, would remain even after the synchrotron emission faded. These remnant structures might be detectable in other wavelengths for hundreds of millions or even billions of years. Eventually, the lobes would merge with the surrounding intergalactic medium. The energy deposited by the jets would have heated and displaced gas across 16 million light-years of space, but over billions of years, that energy would dissipate. The gas would cool. The magnetic fields would decay. And the only evidence of the jets would be subtle irregularities in the distribution of gas and perhaps some residual turbulence. But before they fade completely, the jets might influence the evolution of the galaxy and its surroundings in ways we don't fully understand yet. The energy deposited by the jets could affect star formation, not just in the host galaxy, but in neighboring galaxies that happen to lie within the volume spanned by the lobes. If there are dwarf galaxies or small groups within Alcyoneus's radio lobes, and there probably are given the volume involved, the hot gas and relativistic particles could suppress star formation in those systems. The heating from the jets would raise the temperature of gas clouds, making them harder to collapse under gravity. This could create a dead zone around Alcyoneus where smaller galaxies have their star formation suppressed. Over billions of years, these galaxies would use up their existing gas without forming new stars, eventually fading into systems of only old stars. On the other hand, the jets might trigger star formation in some circumstances. If the expanding lobes create shock waves that compress gas clouds, those clouds might collapse and form stars. This is similar to how supernova shock waves can trigger star formation in nearby molecular clouds. The actual impact probably depends on details we don't yet understand. Different galaxies in different locations relative to the jets might experience different effects. Some might have star formation suppressed, others might have it enhanced. The net effect across the entire region would be the sum of all these individual influences. This is an active area of research. Astronomers are trying to measure star formation rates in galaxies near radio jets to see if there's a systematic effect. The results so far are mixed, with some studies finding suppression, others finding enhancement, and others finding no clear correlation. Part of the difficulty is that star formation rates are influenced by many factors, not just radio jets. A galaxy's mass, its environment, its merger history, and its gas content all play roles. Isolating the specific influence of nearby radio jets from all these other factors is statistically challenging. For Alcyoneus specifically, we don't yet know what galaxies lie within its radio lobes. At 3 billion light-years distance, individual dwarf galaxies would be extremely faint and difficult to detect. We can see the host galaxy and perhaps other bright galaxies in the same region, but cataloguing all the small galaxies would require deep optical surveys that haven't been done yet. Future observations might change this. The Vera Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, LSST, the most comprehensive optical survey of the sky ever attempted. Over 10 years, it will image the entire visible sky repeatedly, detecting billions of galaxies. When LSST data becomes available, astronomers will be able to identify all the galaxies in the region of Alcyoneus, measure their properties, and look for correlations with their position relative to the radio jets. This could reveal whether the jets have had a systematic impact on galaxy evolution in the surrounding volume. Let me bring this full circle to something I mentioned at the very beginning. When you look up at the night sky and see the Milky Way stretching across the darkness, you're seeing our galaxy from the inside. You're part of a system containing hundreds of billions of stars, a disk of matter 100,000 light-years across, rotating around a central black hole. That galaxy is enormous by any human standard. If you could travel at the speed of light, it would take you 100,000 years to cross from one edge to the other. The light from stars on the far side of the galaxy left those stars when humans were just beginning to spread out of Africa. when we were still hunter-gatherers with stone tools. And yet, compared to Alcyoneus, the Milky Way is small. The radio jets of Alcyoneus span 160 times the diameter of the Milky Way. If you placed our entire galaxy at one end of those jets and travelled across them, you'd pass through space enough to fit 160 Milky Ways end to end before reaching the other side. This isn't to diminish the Milky Way. It's our home. It's where we evolved, where our sun formed, where the atoms in our bodies were created in stellar furnaces billions of years ago. It contains wonders beyond counting, billions of stars that might have planets, possibly some with life. But it's a reminder of perspective. From our location on Earth, the Milky Way seems immense. From a cosmic perspective, it's just one galaxy among hundreds of billions, and not even a particularly large one. There are galaxies far larger and structures like the jets of Alcyoneus that dwarf even the largest individual galaxies. This perspective shift is important. It reminds us that we're part of something much larger than ourselves. Not just our civilization or our species, but the galaxy, the universe, the entire cosmic web of structure spanning billions of light years in all directions. And it reminds us how much there is that we don't know. We've mapped our local neighborhood in space, the stars and galaxies within a few 100 million light years. But the observable universe extends 46 billion light years in all directions, and most of it is unexplored territory. We've sampled it, observed the largest structures, but we haven't catalogued every galaxy or studied every region in detail. Let me give you some sense of just how much universe remains unexplored. The observable universe contains an estimated 2 trillion galaxies. That's 2 million galaxies. We've studied in detail maybe a few 100,000 of them. We've measured distances to maybe a few million. We know the basic properties, mass and type and size, for maybe tens of millions. That means we've characterized less than 1% of galaxies in detail. The other 99% plus are out there, most of them too faint or too distant for current surveys to study individually. We see them in deep field images as tiny smudges of light, but we don't know their masses, their ages, whether they have active black holes, or whether they might have radio jets, like Alcyoneus. There are almost certainly more discoveries like Alcyoneus waiting out there, more giant radio galaxies, more unexpected structures, more phenomena we haven't even imagined yet. The universe is vast and full of surprises, and we've only just begun to explore it in a systematic way. Consider this. The Hubble Space Telescope has been operating for over 30 years. It's taken about 1.5 million observations. That sounds like a lot, but the sky contains positions for potentially hundreds of billions of interesting objects. Hubble has sampled an infinitesimal fraction. The James Webb Space Telescope, even more powerful than Hubble, will sample a slightly larger fraction. But it would take thousands of years of continuous observation to survey even 1% of potentially interesting targets. We're like map makers in the age of exploration, who've charted the coastlines of a few continents, but left the interiors blank, marked with "Here be dragons." Except in our case, the blanks represent not land but space. Not hundreds of miles but billions of light years. And the dragons are not mythical beasts but phenomena governed by physics we're still working to understand. The technology we have now, radio telescopes like LOFAR, optical telescopes like Hubble and James Webb, X-ray observatories, gamma-ray detectors, gravitational wave observatories, all of these are tools that would have seemed like science fiction a century ago. And they're revealing a universe more complex and wondrous than anyone imagined. A century ago, we didn't know galaxies existed. We thought the Milky Way was the entire universe. We didn't know about cosmic expansion, dark matter, dark energy, black holes, neutron stars, or any of the exotic phenomena that dominate modern astrophysics. Think about how much we've learned in just 100 years. From believing the universe was static and eternal, to understanding it's expanding and evolving. From thinking stars were eternal lights, to understanding they're nuclear furnaces with finite lifetimes. from having no idea what powered the sun to understanding fusion in exquisite detail. A century from now, what will we know that seems impossible today? What tools will we have? What discoveries will they make possible? We can't know, but we can be certain they'll surprise us, challenge our understanding, and push the boundaries of knowledge even farther. And gravity, the force that shapes everything from falling apples to colliding galaxies, will remain at the center of that exploration. Black holes, the most extreme gravitational environments in the universe, will continue to reveal new physics. Radio jets, powered by black holes and extended by cosmic distances, will continue to probe the structure of the universe. Alcyoneus, with its 16.3 million light-year jets, represents the frontier of what we've discovered so far. It's not just a record holder, it's a signpost pointing toward deeper understanding. Every measurement of its properties, every comparison with other radio galaxies, every theoretical model attempting to explain how it formed, contributes to our knowledge of how the universe works. There's something deeply humbling about contemplating objects like Alcyoneus. The scale is so vast that it's almost incomprehensible. We can do the math, calculate the distances, understand intellectually that the jets span 16 million light years. But truly grasping what that means, truly internalizing that scale, is nearly impossible. Let me try one more analogy to drive home the scale. Imagine you could shrink yourself down and travel inside one of Alcyoneus's jets. You start at the galaxy, near the black hole where the jet is launched. The material here is moving at close to the speed of light, streaming outward in a narrow beam. You travel along the jet, moving at the speed of light yourself. After 8 minutes, you'd be about as far from the galaxy as Earth is from the sun. That's the distance it takes light 8 minutes to travel. The jet is still tight, still bright, still pumping outward with enormous energy. After 8 hours, you'd be about as far as the outer planets in our solar system. After a day, you'd be beyond the orbit of Neptune. After a week, you'd be in the outer reaches of the solar system, where the Voyager spacecraft are now, about a light week from the galaxy. After a month, you'd have covered a light month. The galaxy behind you would be shrinking, but it would still be the dominant feature in your sky. The jet would be widening now, spreading out as it expands into space. After a year, you'd have traveled 1 light year. You'd be at a distance roughly equal to the nearest stars to our sun. The galaxy would now look like a bright but distant object, no longer dominating your view. The jet would be much more diffuse, the particle density dropping as the material expands. After 100 years, you'd have covered 100 light years. You'd be well outside the galaxy, in the halo region, where only old stars and dark matter dominate. The jet would be very diffuse now, a tenuous stream of particles and magnetic fields. After 10,000 years, you'd have covered 10,000 light years. You'd be far beyond the galaxy, out in the space between galaxies. The particle density in the jet would be incredibly low, comparable to the density of the intergalactic medium. But you'd still be in the jet, still within the coherent structure launched by the black hole. After 1 million years of traveling at light speed, you'd have covered 1 million light years. The galaxy would be a faint smudge of light far behind you. You'd be in the radio lobe now, the expanding bubble at the end of the jet. The synchrotron radiation from relativistic electrons would be all around you, though invisible to human eyes. You'd need radio telescopes to detect it. After 8 million years, you'd be nearing the end of the jet. You'd be approaching the bright hotspot, where the jet material is crashing into the intergalactic medium, creating shock waves and heating the gas. After 8.15 million years, you'd reach the end. You'd have traveled from one side of Alcyoneus's radio structure to the other, a journey of 16.3 million years at the speed of light. During that journey, if you had started when anatomically modern humans first appeared on Earth about 300,000 years ago, you wouldn't even be 2% of the way across. If you had started when life first appeared on Earth, about 3.5 billion years ago, you would have crossed the structure more than 200 times. The scales are staggering, and yet, these structures are real. They exist. Right now, as you're reading this, jets of material are streaming out from Alcyoneus at nearly the speed of light, pushing into the sparse gas between galaxies, maintaining structures that have persisted for a significant fraction of the age of the universe. The photons that tell us about Alcyoneus left that galaxy 3 billion years ago. They've been traveling through space while the universe expanded around them, while galaxies collided and merged, while stars were born and died, while planets formed, and, in at least one case, while life evolved from single cells to complex multicellular organisms, to human beings capable of building radio telescopes and deciphering the messages carried by those ancient photons. There's a chain of connection there that's almost poetic. Matter falling into a black hole 3 billion years ago created jets. Those jets produced radio waves. Those radio waves traveled across expanding space for 3 billion years. They arrived at Earth, a small rocky planet orbiting an ordinary star in an unremarkable part of an unremarkable galaxy. They struck antennas built by creatures made of atoms that were themselves forged in the cores of long-dead stars. And those creatures decoded the radio waves and figured out what they were looking at, a galaxy with jets spanning 16 million light years. And they understood, at least intellectually, what they had found. That's extraordinary when you think about it. We're tiny, fragile beings on a small planet, existing for brief lifespans measured in decades. And yet, we can reach out across billions of light years with our instruments and our minds and understand something about the universe that existed long before we did. This is the power of science, and specifically of astronomy. It allows us to transcend our limitations, to see beyond our immediate surroundings, to understand our place in the cosmos. Every discovery, every new observation adds to that understanding. Alcyoneus is not just the largest galaxy structure we've ever found. It's a reminder of the scale of the universe we inhabit, the deep time over which cosmic processes operate, and the remarkable fact that despite our smallness, we can study and comprehend these vast structures. And it's a reminder that there's always more to discover. Alcyoneus held the record for largest galaxy when it was announced in 2022. But as I've mentioned throughout this exploration, we shouldn't expect that record to stand forever. Somewhere in the data sets we've already collected, or in the observations that haven't been made yet, there might be an even larger galaxy waiting to be found. Each record is temporary. Each discovery opens up new questions. Each answer we find reveals how much we still don't know. That's the nature of science. We never reach a final endpoint where everything is understood. We just keep pushing the boundaries of knowledge outward, uncovering new mysteries as we solve old ones. Before you go, I want to ask you a question, and I'm genuinely curious about your answer. If you could travel to any galaxy in the universe and observe it up close, which would you choose and why? Would you pick a nearby galaxy like Andromeda, where you could see individual stars and perhaps even planets, where you could witness the galaxy from outside, seeing its full spiral structure in a way we can never see our own Milky Way? Would you choose a distant galaxy from the early universe to witness star formation at its peak, when the universe was younger and more active, when massive stars were being born at rates far higher than today? Would you want to see a galaxy in the midst of a merger, two massive systems colliding and transforming, creating bursts of star formation and feeding central black holes, witnessing cosmic violence and creation happening simultaneously? Or would you want to see something like Alcyoneus, to stand in the midst of those jets and try to comprehend their scale firsthand? To float in the radio lobes and look back at the galaxy 8 million light years away, realizing you're surrounded by the aftermath of energy released by a black hole billions of years ago. There's no wrong answer. Each choice reveals something about what draws us to astronomy, what captures our imagination about the cosmos. For me, I think I'd want to see Alcyoneus, not just because it's the largest, but because it represents something about the universe that's hard to appreciate from Earth. We see galaxies as objects, as things we can point telescopes at and observe. But Alcyoneus reminds us that galaxies aren't isolated. They reach out into space. They affect their surroundings across distances that dwarf the galaxies themselves. They're connected to the cosmic web, to the large-scale structure of the universe, in ways that go far beyond simple gravitational attraction. Standing in the midst of Alcyoneus's jets, you'd be inside a structure created by a black hole, extended across a significant fraction of the distance to the cosmic horizon. Persisting for a significant fraction of the age of the universe, you'd be witnessing the connection between the smallest scales, quantum fluctuations and particle physics, and the largest scales, cosmic structure spanning millions of light years. That connection, from the quantum to the cosmic, is what makes astronomy so compelling. The same physics operates at all scales. The laws of nature don't change whether you're studying atoms or galaxies. And by understanding one, you gain insight into the other. Alcyoneus, the biggest galaxy humans have ever discovered, is ultimately a lesson in that universality. It's not alien or incomprehensible. It's made of the same matter as Earth, governed by the same forces, operating according to the same principles. It's just operating on a scale so vast that it challenges our ability to visualize. But challenges to our understanding are what drive science forward. Every time we encounter something that doesn't fit our mental models, we're forced to expand those models. Every time we discover something larger, faster, hotter, denser, or more energetic than we expected, we learn something new about what's possible in the universe. Alcyoneus has taught us that radio jets can extend farther than we previously thought, that black holes can maintain activity for longer than we expected, that sparse environments allow expansion to extraordinary scales, and that the universe still holds surprises for those patient enough to look carefully at the data. If you enjoyed this deep dive into the largest galaxy structure ever discovered, consider subscribing. There's always more to explore, always another cosmic mystery waiting to be explained, always another reason to look up at the night sky and marvel at the universe we're part of. The journey to understand Alcyoneus took us from the familiar view of our own Milky Way to jets spanning millions of light years, from the physics of black holes to the structure of the universe itself. And that journey, like all scientific journeys, doesn't end with answers. It ends with more questions, more mysteries, and more reasons to keep exploring. Thank you for spending these 3 hours with me, exploring one of the most extraordinary objects in the known universe. The biggest galaxy humans have ever discovered is out there right now, 3 billion light years away. Its jets extending across 16.3 million light years of space. And now you know not just that it exists, but why it matters, how we found it, and what it tells us about the cosmos we inhabit. The universe is vast and strange and wonderful, and we've only just scratched the surface of what's out there waiting to be discovered. Keep looking up, keep asking questions, and keep exploring. The next great discovery might be hiding in data that's already been collected, waiting for someone with the curiosity and patience to find it.